Alright, hell yeah. So we have dynamics and we have a sample problem. And so this is in the book, you know what I mean? And I don't know, I'm just pretty satisfied about this one because I've been practicing setting up problems and seeing if I can derive them myself. And the setup is the most important part. And so cool. So anyway, so this spins at 6 radians per second. Things that I kind of label, I'm going to label like this theta. I'm going to label this phi. And then we need to know where the slider is. Now, they say this. They want the velocity in relative to this arm. You know what I mean? So this slider can only move this way and this way. You know, so if you take everything out of the equation, all you're going to have is motion this way and this way. You're not going to have motion that way. And but even just that, like that was even just too hard for me. Like I learned that after doing this problem. You know what I mean? And so hell yeah. So for this one, we're going to kind of just divvy it up. We're going to have 10. This is 30, so this is going to be 5 over here. And then we're just kind of going to label things. If this is, this is going to be 10 cosine of 30, which is going to be 8.66. Sweet, so this length right here is going to be 24 minus 8.66, you know, and so on. And then this triangle, well, it shares this triangle. And so if we wanted to find this hypotenuse, well, we're going to take 24 minus 8.66, we're going to square it, and then we're going to square this and square root the whole thing. Pythagorean's theorem, this side squared plus this side squared, square root it. All right, hell yeah. So I guess what we're going to get to, and I'm just going to kind of do this as fast as possible. I want to go to bed. But the general gist is you need to come up with some sort of position equation for B. And I decided to be like, well, why not, why not come over here? So if this is the X and Y coordinate, let's get a position equation from here to here. And I think I end up calling this hypotenuse C. And then we're going to know, so if I have a position vector, I'm going to have, hey, magnitude C. And then I'm going to have cosine phi in the I hat direction. So this is the X direction, the I hat direction. This is the Y direction, the J hat direction. Okay, this is positive, this is positive. And so hell yeah. So this hypotenuse C, cosine of this angle phi is going to be that I hat plus C sine phi J hat. Okay, booyah. So now what? Yeah, so I think we did that. I have my triangle here, and it was just nice to kind of label things. Anything I'm going to put into my calculator, I definitely want to have a label for it. This is a value of 10. Cool. This is a value of 5. No, I call this D as well, because we're going to use it as a variable later on. This 10 I really don't use, else I could have called this a letter as well. But hell yeah. So this is A, D, B, C. And if we go back to... Oh yeah, and then it was kind of cool. So here was our position equation, and I was just like, oh, well no duh, because we have some things going on. Because this cosine of phi, I've done this in other videos. Anytime you have like cosine of an angle, or sine of an angle, or tangent of an angle, these give you ratios. You know what I mean? I would actually spell it out. And I'm going to do this every video, you know what I mean? This is the only way to learn statics, trigonometry, is just like when you find something, double down on it. Be like, oh hell yeah. And then figure out what it is for a bunch of different things. So if I see cosine of an angle, this is the ratio. And so let's go to our triangle, because we're going to have C, and then we're going to have cosine of this angle phi. So cosine, what I do is like, hey, if this is the angle, make some sun rays. Sun is shining on the sine end. So this is your sine component, this is your cosine component, your adjacent. So we're going to have, and then the cosine of the angle. For cosine and sine, these are percentages of the hypotenuse. So you have the hypotenuse, and then you have just a percentage of it. So whatever this C value is, hell yeah. Then we're going to take the percentage. It might be 5%. It might be 95%. And where you can see right here, look at this. Like if this is your hypotenuse, this looks like 95%. You know, if this is your hypotenuse, this looks like 86.6%, just because we know it. It's, you know, but hell yeah, if this is 100, you know what I mean? This is 50. Hey, this is 50, and this looks like about 80 to 90. Okay, booyah. Okay, so cosine of an angle is going to be B divided by C. So that's all I was getting at. So sweet. So you're going to have C times B divided by C. Oh, well, doesn't C just cancel? Holy Toledo. And the same thing here. You have C times sine of this angle, and you're going to have D divided by C. So sweet. So and I do that. So we do that here. So that's kind of what happened, and we're going to have BD. So this is going to be, so just remember that BD. So my position vector up to here is going to be, well, and then it's just obvious. Well, of course it's going to be this length, B, and this length, D. So this problem just really was helpful, being like, hey, let's overcomplicate things and just see how many things just kind of cancel and annihilate themselves. So hell yeah. So for sure. So obviously, if we're trying to find the position vector up to here, well, it's just going to be this length in the I direction and this length in the J direction. And booyah, B and D. All right. Okay, so, and then there was going to be another thing, though. For sure there was. Oh, yeah. Because, cool. So now we know where this location is in terms of the x-coordinate and the y-coordinate. But the problem statement says, hey, we want to find this position relative to this angle. You know what I mean? So we need a new coordinate system right there. We need an x prime and a y prime. We need an I hat prime and a j hat prime. And so now we need to figure out if we have this position vector, you know what I mean? And this is our vector. Here's our two components. I like to do like a darkened end arrow and then just an open-faced arrow, just so you kind of know, like, hey, this is the actual one, and then these are the components. Okay, so we need to know how much of this thing is in this direction and how much of this thing is in this direction. And you can just obviously see that it's all in that direction, but I'm just so curious to even make my own problem where you have like you know, you have an axis that's not in the x and y, but also not relative to the thing that's, you know, so that's, we're gonna figure out, well, how do we take this component and make sure it's in a different, which has a I component and a j component, this x and y, and how do we take that and see how much is in this direction and how much is in this direction? Visually, we see it's all in this direction, but what's the method to do that? So what we do is we use the dot product. So again, we have our vector. I don't know if I wrote it, but we have our vector, and that's going to be b I hat plus d j hat. Oh, so there it is. We got a lot going on. All right, so what we do is we have to dot it with, and you got to do this twice, which is kind of a bummer. That's why I kind of have it twice. So here is taking this whole vector, these two terms, and dotting it with, what we're trying to do is you get a unit vector in this direction. So how do we do that? Well, I don't know, just draw a big arrow in this direction and label it 1. And if that's always confusing for you, I don't know, label it 1 meter, or just label it 100. But you would have to divide by 100. I don't know. But if you label it 1, so now we're going to see, hey, what are the, so we're going to label, so the hypotenuse is 1. The bigger number is 1. And hey, we got an angle here of 30. So it should be pretty easy to see, like, hey, isn't this just half? Like, isn't this just 0.5? And then isn't this just 0.866? And then the other thing is like, well, how did we get this? Well, this is going to be the hypotenuse sine theta, and this is going to be the hypotenuse cosine theta. And again, it's the bigger number multiplied by this percentage in this direction. So we have 50%. In 50% of the hypotenuse in the vertical direction, 86.6% of the hypotenuse in this direction. And if this vector is 1, these are just percentage. See how 0.5 is equivalent to 50% and 0.866 is equivalent to 86.6%. Okay, sweet. So now we have this unit, and I hate this term. I never know like where to put. So we have this unit vector. It does have a hat. That's like the vector hat. You know what I mean? Do this, you know, just to show it's a vector. Or you can do a little hat maybe. But we have a unit vector in this prime direction. In the I prime. In the I prime direction. Holy hell. So how do we donate yeah, I'm just going to do that. So cool. So there it is. And we're going to, and it's going to have, even though it's in the prime direction, it still has, check this out. So it's still going to be 0.866 I hat plus 0.5 j hat. So that's what I'm getting at. It's in the prime direction. Cool. It's a unit vector in that direction. But we denote it by its original Cartesian coordinates. So just the normal x and the normal y. Cool, we got that. But now you actually have to come over here and get this one. And this was the tricky one. Because, okay, and let's go back to here. Because this was just cosine of this angle phi. So I said this is cosine phi plus sine phi j hat and then I hat. Hell yeah. So we're done with that one. But now, how do we get, so yeah, so that kind of threw me for a loop. I was just like, well, how do we actually get this? So this was that 30-degree angle, but how do we get all the way up to here? It's a 90 plus 30. You know what I mean? I can get to that aspect. And then, so what I did is just like, well, I see that I used the Zorro technique. I know what this triangle is. It's BDC. And so what I'm going to do is draw like this horizontal. And I know that this is phi. And if this is like a Z, I think it was like a Zorro. I don't know why. It's totally like a Zorro thing. And then, so this is phi. And then anytime that you have angles that, you know, are coming in like this, well, obviously, this should be the obvious. Like, okay, that's phi. And then we have 90 right here. And then we have rotated, so and we know that this is 90 right here. So we have this 90 that is rotating up. And so we do know that this angle is phi. Cool. But what we want to figure out is, so again, we're going to draw a vector of 1. And so see how here we're going to go up quite a bit. It's always good to get a visual representation. We're going to go up quite a bit in the y direction. And then we're also going to go over in the negative. We're going to go negative in this direction. Okay, so so what I did is I said, well, if the shorter side is D and the longer side is B, like this side is B, then I can come up here and be like, okay, this is the hypotenuse, this is D, this is B, and so what do we do? Oh yeah, and we know that these so it's kind of interesting. This is the other thing from, I'm going to redraw that triangle. Whoa, no, I'm getting sloppy. But the other thing from statics is that, yeah, this could be like 50. You know, I mean, hey, just let's throw a number on it. This could be 50, this could be 45, and this could be like 17, 18. You know, it's always good to get a visual representation. Just call the hypotenuse something, and then start labeling the other ones. But if you want a unit vector, if you want to call this 1, an easy way to do that, well, I mean, basically, if this is 1, you want to know the percentage of this, you know. So if you said this is 100% or 1, you could be like, well, let's just guess. This looks like 86 or like 0.866, either 86.6% or a ratio of like 0.866. This looks like 0.5 again. Okay, hell yeah. So, but how do we do that just with these lengths? So you can say that what I do is, let's just take this one. So we have B divided by C. What does that give us? So if here's our angle phi, this B is the cosine component, so it's cosine divided by the hypotenuse. Well, isn't that just cosine of phi? That's going to be B divided by, it's going to be this side divided by the hypotenuse. And don't we know cosine is just the percentage of the hypotenuse? So yeah, it's like this one gets way overlooked, that you can just take this side, divide it by the hypotenuse, and that gives you that ratio. So so sweet. And so for this unit vector, in the y direction, so we have our unit vector in the I hat. We're getting hella sloppy, but I'm just either not going to do this or I'm going to do it. So we're going to do it. And then so what we want to do is we want to get this unit vector, and hell yeah, so it's going to be in the positive y, but it's going to be in the negative I. So so if we come over here, it's going to be, so d divided by c. So that's going to be the ratio in the negative direction. So we have negative d divided by c. We're going to go up b divided by c. And that's going to give us a unit vector. You know what I mean? So we're going to have basically 0.866 and then negative 0.5i. So there you go. So now we have, I guess I'm going to write it again. We have a unit vector in the j prime direction of negative 0.5i plus 0.866j. Cool, which would be negative cosine phi of I plus sine of j. But then I was just like, well, hell yeah, let's just use these with BC, DC, and then negative DC, BC. You know, have them with these letters. So I found that to be very useful, just because I don't have to rewrite them. But then when we go take the dot product, it says, hey, we have this vector BD. We already got that. It's over B up D in that direction. And we're trying to find the components of it in this direction and that direction. And so what we do is we take that vector and then dot it with one of these to get the direction in the I would call it the x prime direction, the I hat prime direction. So you have to take the whole vector, dot it with the whole, with this one, you know, the unit vector in that direction, and then you get the component, the number in this direction. Then you got to do the whole thing over again. You got to take this vector, and then you got to dot it with the unit vector in that direction. So it's just 1,000 steps, and just the fact that you have to do that is like the most maddening thing. I hate it. You know, there's no two ways about it. Changing directions is just like, I don't want to take the dot product twice. But anyway, so that's what you do. So if we take the dot product, we're going to do this one first. It's just you take the similar, so if this is an I hat and this is an I hat, cool, you get to multiply those. These are j hats, you get to multiply those. And then you're just going to add. So we're going to multiply these and add them to the multiplication of those. And you get a scalar. Again, you just get a number, but in this case, it's going to be the number that's going to be the magnitude in this new I hat prime direction. Cool. So we're going to b times b divided by c. Sweet. So we're going to have b squared divided by c plus d squared divided by c in that I hat prime direction. And then let's do the other one. We're going to have b times d. So we're going to have negative b times d divided by c plus b times d divided by c. Okay, in the j hat direction. And you can see that negative, these cancel. This one's negative, this one's positive. And that was just like a real cool moment. I was just like, hell yeah. Alright, so now we have all this in this direction. So I was just like, well, what? Cool. And I bet you, I was just like, huh, I wonder what this is. Can we kind of simplify it? Because if we see, like, what is C? You know, again, we have this B direction and this D direction, and we're saying C is B squared plus D squared square root of that. You know, so that's what we have, and so let's see what I did. I went from here, and then I was just like, oh, we can divide by C on both of them. So I'm going to do B squared plus D squared. But I can divide by c. We just got c right there. So that's the c's on the denominator for both of those. And sweet. And then I was just like, well, this looks like I could factor it out. This is almost like x to the 1. And this is the same down here, but it's x to the 1/2. So this gives me the square root of b squared plus d squared. And I was just like, oh yeah, super familiar. That's just c. So after all of that, it was just c, which was... So we have C in the I hat prime direction. And so that is, that was that. Alright, hell yeah, I got confused because C is still, all we know C is as it's B squared plus D squared square rooted. Because we know these two sides, we still don't know the hypotenuse. That's C. So C is B squared plus D squared. And taking the square root of that, we know that B is that 24, you know, minus that 8.6. We're going to square it, and then D is going to be 5. But now here is where you actually need to get your vector. So we're going to say, yeah, so I guess I'm going to, because all I did was get to here, and I saw it, and I didn't want to write it again. But now we have this in the I hat prime direction, and oh, bummer. I'm gonna have to go back. Yeah, that's and I should print out another sheet, but I'm not going to. So with these problems, like, hey, this is your theta, but this is your theta naught. You know, so we have theta naught is 30 degrees. And we're going to have a change in theta. That's the definition of angular velocity. It's a change in 6 radians for every change of 1 second. So 6 radians per second. So theta as a function, what we're trying to get is theta as a function of time. That's going to be theta naught. And then in this case, we're going to subtract omega t. And man, like I never knew what the hell was going on, and I'm just sorry, I just don't want to explain it more. But I guess I just did. That's literally the definition. Angular velocity is change in angle, change in time, d theta dt. And sweet, so that is the change in theta. So we're gonna, theta as a function of time is the original initial theta plus the change in theta. And that is the change in theta. And the change in theta is the omega times, but if angular velocity is change in angle divided by change in time, you have to multiply by the change in time. So there you go. So change in angle, change in time is 6 radians per second multiplied by the change in time of t, and that's going to give you the change in angle. Cool. So that's where that comes from. And so now Hell yeah. So just all these, you know, this length as a function of time will be 10 cosine of that initial angle theta minus omega t. So that's kind of where we're getting at. So this A is going to be 10 cosine theta naught, that's the initial angle, that's just a scalar, a constant, minus omega, this doesn't change, but t is what's changing. Sweet. And then so we just do that for all of these. You know, this one's going to be 10 cosine, this one's going to be 10 sine. Sweet. If this is 10 sine, well, and then this one's going to be the whole length 24 minus this 10 cosine. And then so those are the two, that's B and D. Sweet. And so that's what, both of these we're going to square and then take the square root. And this is our position equation. Cool. So now this problem says, hey, what's the velocity? So then you just do the, you know, the hocus pocus, you know, I don't know. You take the derivative of it. So you take the derivative of this equation with respect to t. Now if this equation was just 3t squared, the derivative of it would just be 6t. But it's not. It's a humdinger. So that's where I wanted to make the video, because I don't know, like this isn't polished, but I have a decent system. Just within this page, I took a very complex derivative twice. I took got the velocity and I got the acceleration. So no, there they both are. There's the velocity, there's the acceleration. So let's begin. So this function is a square root, and then inside do we have this squared plus this squared. Sweet. So the first thing that we do is we see that it's a square root. That's, you know, you could just say it's this to the 1/2. And then so we're basically taking the derivative of that, you know. So like I wouldn't even call it u substitution. I swear the second you say u substitution, like my brain shuts off, but just treat it like it's, I don't know, just treat it like it's hella simple. You're going to, you know, forget everything inside for the time being, and you're going to bring down the half. So we're going to have 1/2, and then it's all that stuff to the negative 1/2. Sweet. And you're done with that aspect. All right, but now you do need to take the derivative of the inside. Okay, we got two elements. Let's just start with the first one. Oh, sweet. It's another junk in the middle, and then to the 2. So that's what we're gonna bring down the 2, and then we're gonna take the junk in the middle, and then to the 1 power. So we're done with that aspect. But then we got to take the derivative inside. Derivative inside, well, this just goes to 0, and we're gonna take the derivative of cosine. So that's where you need to know cosine graph goes like this. It's negative sloping, and so we're gonna get negative sine. You know, it's gonna turn that sine into a positive. So we're going to have 10 sine, oh yeah, but you got more junk in here, you know what I mean? So you got negative, negative 10 sine of the junk in there. Cool, we're done with this. But now you got to take, multiplied by the derivative of that junk. But this is 0, this is just a constant, and this is just negative omega t. So you got t to the 1, bring down the 1, you just got negative omega. Sweet. So this whole thing is going to be, and you know, we took this negative to a positive because we changed it to sine, but then we're going to bring it back to a negative. So we're going to have negative 10 omega cosine the junk inside. Sweet. Cool. And then you do the same thing here. Derivative of sine is cosine. Enough said. And then we're going to have to take the derivative of the junk inside. So you're going to have 10 cosine junk multiplied by negative omega. So you're going to have here negative 10 cosine junk inside. Sweet. Yeah, negative 10 omega cosine, and then that stuff. All right, sweet. And so that's what we have right there. And then we're basically kind of done. We took the derivative of the inside. Whew, that was ridiculous, you know, and we did it. And now this is what it looks like if you put it all together. But why write all this stuff? So then I just kind of came up with a system that I'll work on, you know, in future videos. Is like, well, let's write all those things down just once, just so we have them, and then we can reference them. So we have this square root of all this stuff inside. I'm going to call all the stuff inside 1. I mean, I should have just used letters, but it was kind of fascinating to use numbers. I kind of like to use numbers, and then I went back and added letters next to them, and then in my calculator I used the letters. Sweet. So there you go. So this whole thing inside is just 1. So we're going to have 1/2, 1 to the negative 1/2. Sweet. And then, but then you're going to have to multiply it by that derivative. The derivative was, hey, this is the inside. Bring the 2 down. And then we're going to have the derivative of that. That was going to be... Oh, no. Yeah, bring the 2 down, and then multiply it by the inside. But then multiply it by the derivative of the inside, which was that. So, and then you're done. Okay, and now over here, bring the 2 down. Multiply it by the inside to the 1 power, and then you got to multiply it by the derivative of the inside. So you can just do a ton of stuff in just a small amount of space. Alright, hell yeah. So that gives us the velocity equation. But now we got to take the derivative of this. And you can see we have 2 products. So we have to take this times the derivative of that plus this times the derivative of that. And so how I started is just like, well, let's just take the derivative of this first. It just seems simpler. So I'm going to bring down the negative 1/2. That's negative 1/4. 1 to the negative, and this drops by a power, negative 3/2. And then we got to, that's the derivative of this, but then we would have to multiply it by the derivative of the inside. But we just did that. The derivative of the inside is this thing. I'm going to call it 6. So sweet. So we're going to have derivative of this times 6, you know, because we got to do that. And then, so this was the derivative of this was doing all that stuff, but then you had to take the derivative of the inside, which was that. Sweet. And then, but then you got to take this times the derivative of, why is there 2 here? This should be way easier. Okay, first I'm going to take this. Okay, that's one of the 6's times the derivative of this. We just did that, but then you substitute. But we got to take the derivative of the inside, so you're going to get another one. Cool. Plus this. Now we got to take the derivative of this craziness, but it's not too bad. We have a 2, and then we got to take. So we're going to do 2, and then we're going to take the derivative of this times that. What's the derivative of 2? We already did that one. The derivative of 2 was 4. So we're going to have 4 squared. But then we got to take plus 2 times this times the derivative of that. This one. So we need to take the derivative of this. We have a sine. Sine goes this way. Slope of 1 is going to be a positive cosine. So the derivative of this is positive cosine. We do have this negative though. So we're going to have negative 10 omega cosine of the stuff inside, multiplied by the derivative of the stuff inside, which is a negative omega. So we're going to have, that negative is going to be a positive, so we're going to have positive 10 omega squared cosine of that junk inside. Hell yeah, so that's the derivative of 4. Positive 10 omega squared cosine junk inside. Sweet, so that is number 4, and that was the derivative number 4. We're going to call it 7. So booyah. So we did the first times the derivative of the second. Actually, we did this in reverse. We took this times the derivative of 2, which was 4. So we get double it. Then we're going to take this 2 times the derivative of 4, which we just turned into 7. We just did that. Okay, same thing here. Derivative of 3 is 5. So we're going to take this times the derivative of that. So we're going to have 5 squared plus this times the derivative of that. Derivative of 5, let's do that one and almost be done. So we have a cosine graph. Cool, it's a negative slope. So we're going to have a negative sign. That's the derivative of cosine, negative sign. We do have this negative, so we're going to have positive 10 omega sine of this. And then we got junk inside, so we got to multiply it by the derivative of the junk inside. So again, we have positive 10 omega sine junk inside. But this becomes a negative omega. So we're going to have a negative 10 omega squared sine junk inside. Negative 10 omega squared sine junk inside. All right, sweet. And then that's that. That's going to be number 8. So booyah. So that was the first times the derivative of the second, and that's what we did. So hell yeah. So then I just rewrote this 1/4, and then I switched everything to letters. So the 1 was E, 2 is F. And so I just switched it to letters, and I was able to put it into my calculator. And that's why I just wanted to make this video, because I made no mistakes. And I did this my first time around. So sorry for just such a crap video. But I will do this process again and streamline it. But hell yeah. And I think I really like boxing it. I've just gotten used to boxing in letters. You know what I mean? It doesn't take that long. And, I could just use A, B, C, but I just don't think I would recognize that it's in my This means that it's hella in my calculator. If it's a letter, that's why I use numbers, because they weren't in my calculator until I put them in. And so that was kind of it was just fascinating yeah, that's why I use numbers. So I definitely, but boxing things in is just, you can totally see that they look nice, and then you can see that this is a value of 2. These are exponents, but boxing in a number or letter can just represent something where you would run out of paper to try to get it all in. All right, hell yeah. So big derivatives, and I'm pretty satisfied with this one. Thanks for joining me, and that's a video.